Hello and welcome back to Unit 11. In this part of Unit 11, we're going to learn about the moment of inertia. So what is moment of inertia? Well, remember how an object's mass determined how quickly a force could change its velocity, getting back to Newton's second law that the net force equals ma? The moment of inertia serves the same role for rotations. How easy or hard is it to get something to rotate? And from this standpoint, you can think of the moment of inertia as the angular equivalent of mass. Okay. So, a couple of questions. Is something that is more massive harder to rotate? I don't think anybody is going to hesitate to say yes. Okay. Is it harder to rotate if the mass is further from the axis? So if I hold a stick in the middle versus holding a stick at the end, does that change how easy I can get it to spin? The answer there is yes. So the moment of inertia is going to depend not only on the mass, but on how that mass is distributed, specifically how far is it from the axis of rotation. Okay. So if I have a collection of objects, so maybe I think about it being two masses on the end of a very, very light string, I can calculate their moment of inertia. In general, for a collection of masses, the moment of inertia given by capital I is going to be the sum over each mass multiplied by the distance it is from the axis squared. So in this case, if this is M1, that would be R1 and R2 for M2. Now, the masses do not have to be situated equally from the axis, and the axis can be anywhere. I could consider rotating the same distribution of masses about this axis, in which case this would be R1 and R2 would be 0 because the mass is at the axis of rotation. As we've seen numerous times, if we're going from a summation or a collection of objects to a continuous object, we move from a summation to an integral. So in this case, I will equal r squared dm, where dm is a little piece of mass. So if I have an object, I would take and define a dm in that object, a little piece of mass, and by integrating, I'm adding up all these little chunks of mass. R in this case would be the distance from the mass piece that we're looking at to the axis of rotation. So if I think about rotating about this axis, then R would be that distance. Okay. Now, luckily, the moment of inertia for standard continuous objects have been calculated numerous times. In the next part of this unit, I will show you how to do some of those calculations. But they're in tables. So here is a table of common moments of inertia. So we can see if we have a thin hoop of radius r through the center, the moment of inertia is the mass of the hoop times the radius squared. If, however, we rotate that same thin hoop instead of through the center, but through this axis like this, then we get a different moment of inertia. And in this case, the width of the hoop also matters. We can look at a solid cylinder and a hollow cylinder. We will do these calculations in the next unit. We can think about a uniform sphere. That would be this calculation, which we'll do the next unit. And we can think about a rod of uniform length, rotated about the center or about one end. And we do one of those two calculations in the next unit. I don't remember which. And lastly, the last one listed there is a rectangular thin plate. Okay. Again, in the next part, I've been saying unit, but in the next part, we will do 3 of these calculations and get these formulas. In the meantime, I want to focus on these two because it's the same object, just rotated about a different spot. Okay. So copying those two entries over, the long uniform rod of length L about the center of the mass, or the long uniform rod of length L about an end. And what I want to do is subtract. So I'm going to take the moment of inertia through the center of mass and subtract the moment of inertia about one end. That is going to be 1/12 ml squared minus 1/3 ml squared, which is ml squared times 1/12 minus 4/12, or that works out to be negative 3/12 ml squared. I screwed that up. Let's try again. 1/3 is not 4/12. Yes, it is. Yes, it is. Never mind. I did not screw it up. Okay. So ICM minus IN is going to equal negative 3/12 ml squared, which is negative 1/4 ml squared, which is negative 1/2 squared ml squared. Now this number is interesting. Okay. That number is interesting because that's the amount that the axis have been shifted. It's been shifted half the length. It would be better if I wrote this as this, L over 2, the quantity squared times the mass, where L over 2 is the distance from the center of mass to where the new axis is. This gives us an interesting result. And while we've looked at it specifically for this system, it's true in general. The moment of inertia about any axis, I'm just going to call it axis, is the moment of inertia of the center of mass minus, plus the mass times d squared. Okay, what is d? D is the distance from the center of mass to the axis. If I rearrange this and take ICM minus I axis, that gives me negative MD squared, which is exactly the result I got up above looking at the long uniform rod. Lastly, what do you do when your object isn't just a rod or isn't just a cylinder? It's a collection. Well, the answer there is you add it, just like you would mass. Remember, moment of inertia is the angular equivalent of mass. So I can add these all up. I just have to be careful when I do it to make sure that I keep my axis the same. So what I have here is I have a sphere attached to a long, thin rod. If I go back to the table that I gave you a couple slides ago, we find that the moment of inertia of a rod about the end is 1/3 ml squared, where L is the length of the rod. Okay, And I'm going to make this a little m sub r for mass of the rod. Okay. If again I go back to that table, I find the moment of inertia of a sphere about the center of mass is 2/5 mr squared. And again, I'm going to subscript this with an s for it's the sphere, and r in this case would be the radius of the sphere. Don't need an s on that one. Okay. Now I have to keep my center or my axis the same. So remember, this was the moment of inertia of a rod about the end, but this is a sphere about the center of mass, but we're not rotating about the center of mass. The center of mass would be down here, or drawing my axis properly, let's try it again, would be down here. I need to shift the moment of inertia of the sphere from being about the center of mass to being about where my axis is. To do that, I can use the parallel axis theorem. So the moment of inertia about the axis will be the moment of inertia about the center of mass plus the mass times the distance between the center of mass and the axis squared. So this will be 2/5 times the mass of the sphere, r squared, plus the mass of the sphere times d. And what is d? It is the distance from the center of the sphere all the way to the axis, which is r plus L. So d is this entire length. Okay. I can now find the total moment of inertia of these two objects combined by adding them together. So that works out to be 1/3 times the mass of the rod times the length of the rod squared, plus 2/5 times the mass of the sphere times the radius of the sphere squared, plus the mass of the sphere times the radius of the sphere plus the length squared. As I said, in the next part, we're going to do a bunch of examples calculating numerous of the moments of inertia on the table that was provided in this unit.